In this talk, I will be basically presenting a work from Sebastian van Zelst, who is a PhD student in our group, but was in the last minute unable to attend. But I'm a co-author of this work, so it's my duty now to present that. This is a collaboration with Alfredo Bolt, Bouden van Dongen, and Will van der Aalst. So all of them in our group in the Technical University of Eindhoven. And in this talk, I want to address the topic of online conformance checking for dealing with streaming event logs. So how to correlate streaming event logs with models that are built above those ones. For that, I will try to introduce slightly the area of process mining through a running example, and then I will come closer to the definitions of conformance checking and then prefix alignments. Yeah, so I will be using an example from the help desk of an internet service provider, where we assume that we have some ERP system that is able to register all of the activities that are happening. So like the phone calls and also the activities that are being done in order to get some technical problem solved by customers of that ISP. And so this is one possibility of the log. How could the log file look like? So we have a call ID that is representing the case ID that we want to deal with, and it's connected to some customers, but one customer can call multiple times. And then we have an activity that is being registered that is related to that particular case ID. For example, registering the call or taking the call, checking the line, resetting a modem, and so on. And each of these activities has a particular timestamp and a resource that is implementing it. So this is a different case from the usual task where we have multiple attributes that we can do whatever we want with them, because in this case we have resources who are concurrently working on multiple tasks. So we have the timestamps and the resources, and they might reflect in many cases some kind of bottlenecks that cannot be extracted using typical data mining solutions. Yeah. So those are the three main tasks of process mining, and all of them contain the first citizens in the field, so the log file on the left-hand side and the process model on the right-hand side. Yeah, so in the first task, we try to extract some knowledge from the log file in order to design some model that is reflecting all of these concurrencies in a very compact way. And there are multiple ways for doing that. It's not the task of me now to explain that because it's too much information that are not relevant for us, but Petri nets are one example of them. So they are very compact, they can represent a lot of loops and concurrencies, and they can show things that are happening together at the same time better than, for example, state charts. The other task is conformance checking, and in this task, you can have an example that some company is having an idea about their business, how it looks like, and they try to summarize it in some model. And then after a while, they want to see whether that model still holds. So they try to check their log files and see how much they are conforming that particular model that they have in mind. But this can also be used by, for example, auditors if they want to check that a particular bank is still following what they have from rules in mind by checking the log file and comparing it to the model that they are assuming that this bank is following. And the final task is enhancement. So that could be, for example, detecting bottlenecks by by applying the log file over the model, seeing where are the bottlenecks happening and doing some actions, or even predicting when some bottlenecks might be happening in the future. In this talk, I will be focusing on conformance checking. So that means I assume that I have a particular model that I am starting from, and I have a stream of events that are arriving, and I want to see how much conforming are those events or the stream of events with my model. So this is a very simple way about conformance checking. So the person who made those barriers, or whatever you want to call them, assumed that the bike driver should follow that model. Like they should definitely be walking while crossing that road, because this is the model that they have in mind. But reality might change, because you might have some people who are really not following that model, right? And that is exactly the case where we see multiple cases from an event log that are not conforming or following a model that a company is assuming that everyone is following. So this does not need to be in a bad way that we want to detect those who are not following the model. It could be something that is desired by the people who are working on that information system, but it's not an optimal way. So the original model is not optimal. So you might need really to adapt to the new requirements. For example, completely take that barrier away, because people will anyway find a solution to, they need to pass this road on their bikes. So this is exactly the problem that we are dealing with here. So, so this is one example of a process model that is related to our running example from the ISP help desk. So this is a very simple Petri-net that we don't need to understand the details of it. We just need to see that this is how the process goes. So here we have. Can you hear me now? Yeah. Okay. So here we have at the beginning we register the system registers a call, and then someone should be physically taking that call. And this offers the possibility of concurrent tasks. So those two activities, resetting the modem and checking the line, can be done in parallel. So that means I do not need to do them sequentially by locking one of them until the other one is done. This is possible to be represented using batteries. And then once those two tasks are done, we check the connectivity. And here, these represent three choices. We can either register success, that means it was successfully finished, or dispatch it, or do we do this loop back to retesting the check line and reset it again. So this is a model that the company who is caring about the help desk started by having this model, and they want to check whether all of the cases are following that model. So as you see, we have possibilities for concurrency, and we have also possibilities for having loop backs, and we have also a possibility here in P6 for having multiple choices. So this is now, we are revisiting now our log file, and we see here that we have, in the log file, we might have an overlapping between multiple cases. So what you see below is the log file summarization using now not the register call and take call, but the shorthand. Names A, B, C, D, E, G that are related to the call ID 175337. So that is our case ID. And now what we want to do is simply checking whether this event log this trace from the event log is conforming with the model that the company has in mind. And this can be simply done by starting from the start and observing whether this is following exactly the model. So we have E, and then we have B here, so taking the call, and then we have the concurrency. That means C and D can be done in any order. So we have C, D in the event log, so that's fine. And then we have checking the connectivity, E, and then one of the three choices, so either G or H or F, can be taken. So we have in the log file G, that means this log file, this trace from the log file is following exactly that model. But in reality, as we have seen, we might have multiple cases where that is not the case. So here is an example where, for example, we have A followed by D, while we are expecting, according to the model, to have first a B, where we are taking the call. So we are directly jumping to D, which is resetting the modem. This might be due to many reasons, but this is something that we want to see in an online setting. So as a solution for that, in the offline cases, we have alignments. So alignments are basically having this style. So the upper row is reflecting the log file, and the second row is reflecting the data from the modem. And whenever we have a green, in this example, whenever we have a green column, that means it's a synchronous move. So it's something that is expected by the model, and it's available in the log file. And the red column here represents something that the model dictates, but was not available in the log file. And that's why we have those two skip. This skip simple where we are making only a move on the model side, and the orange column is representing the other way around. So something that appeared in the log file, but not dictated by the model itself. So yeah, there might be, of course, multiple ways if we are having the upper row log file and we want to map it, so to say, to the process model. There are multiple ways of doing that. So this is actually one way for doing this, but it could be some other ways. But usually we try to minimize the number of skips that we are having. So we want to have as much green columns as possible, because the other ones are expensive. And we show in the paper that we refer to other works which are showing that this problem can be reduced to a shortest path problem, and many algorithms are using, many solutions are using the A* algorithm for that. So this is available in the paper. So the alignments for the offline settings are very good, but they have a very major disadvantage when we want to apply them in online settings. They are expecting always that we need to apply on the model size some trace that is accepted by the language of this process model. So we need always to see all the log file till the end, the trace from the log file, in order to map it to the process model. In the streaming settings, this is not possible. So we only see, for example, for this particular case, we see something. We see, for example, register call followed by check line. And we need to take action at that point. We cannot wait until the end of our case ID and then say that there is a deviation. We want to signal something when we see some deviation from the model in the real time, or possibly not with a lot of delay afterwards. So that's why we do not use the alignments in their settings, and we use prefix alignments in this work for dealing with event streams. And simply prefix alignments, they relax the requirement that the bottom line needs to be a trace that is available in the language of the process model. So if we receive, for example, A from the event stream, it's enough to locate A using the prefix alignment like this. So here we say that, okay, we were able to find A in the process model, and fortunately it's exactly the first activity after the start. Then we have this synchronous move, and we have a green column there representing A. And assumption is that the rest of the alignment looks like that. So this is the worst case of the rest of the alignment here on the right-hand side. So if we receive now D after A, then we start to search, okay, after A, what are we expecting? We are expecting B, so we have D in the log file. What to do now is to search whether we have at all a D in the process model, and we see it, and then the solution would be to simply make a model move where we skip D, or we can do that actually in two ways. So either by making this model move, or by doing this label move. Yeah, so, and in this case, we show also that we can have multiple alignments and prefix alignments of the same trace. In this case, they have the same cost, because in both cases we have one non-green column. So that's the basic incremental scheme that we are using in our approach. So it's an abstract explanation of this algorithm here, but it's formally described in the paper. So what we do basically is we receive for each now a new activity from the stream. We first try to directly do a synchronous move. So this was possible, for example, here with the A. So we have received A from the stream up, and we tried to directly map it to the model, and we were lucky because that was possible. But if this is not the case, so if we were unable to do a synchronous move, then we try if the activity is not an unknown activity, so that if the activity is available in the process model, but it cannot be executed directly, like D here, for example, then we perform a prefix alignment search problem. And here we have used, again, the A star as a representative for a shortest path problem. So we try to look to what is the shortest path that we need to follow in the process model in order to locate D in its correct place. And we discover here that this is the case. Yeah, and in the worst case, if this is not possible at all, so we have, an activity that is not available here at all. So, for example, if we have X, completely activity that is not available in the log file, we directly add the label move. So we add the worst case scenario there. So this is an example about that. So this is first, we could achieve a synchronous move for A because we have seen it from the stream. And after receiving D, we have tried to find the shortest path in order to locate it. And here we have two different, but equally, the cost of them are equal, of those two prefix alignments for AD. And yeah. So basically, this is the basic incremental scheme that we are using in our approach. And we are now trying to add some parameters to this approach in order to make it a little bit more efficient. The first parameter is the upper bound. And here we assume that we are making use now, in this case, of the fact that if the cost of the timestamp I, if the cost was something which we have there now, so it was one red column, and we received an E after that, then the worst case for the cost of I plus 1 is adding this skip. So that means we know that the upper limit for aligning P in the correct place is this case. So this is the worst case. And thus, while searching for, in using the search algorithm, we can directly prune out any costs that are above this one. And this is very important because it, as we will show in the experimental evaluation, it is saving a lot of space and it is saving a lot of space, and the number of states that are visited is considerably reduced by taking that into consideration. So that is one parameter that we are adding to our problem, and the other parameter is the window size. And this is basically, we are using this one to limit the starting point of the search. So whenever we are receiving a new item from the stream, we usually now go back to the beginning of the stream and try to align, or to prefix align all of that part of the stream. Now we say we relax that a bit and we try to go by a window size in the previous steps like 5 or 10 or 20, and definitely not to the starting point of the stream. So those are the two parameters that we are using in our experimental, that we are using to try to make our approach more efficient. Yes, and to the experimental evaluation, so those are the settings. We have used artificial data sets and real data sets. Actually, a single real data set. So for the artificial data set, we have generated a process model first, and then we have used that process model for generating 18 different streams. So, we have generated out of each process model one event stream, and by doing so, it's 100% fitting the model. So that is not useful for us because we are trying to do the conformance checking. That's why in the next step we added noise to an artificial noise to the event stream. So the adding of noise means that we sometimes added some activities that are not available or deleted other activities and so on. So this ended up with a huge amount of events, around 44 million events that we dealt with. In the real data set, we had an event log from Dutch hospital treatment of patients suspect of having sepsis, and we had around 15,000 events divided over a little bit more than 10,000 cases, so 10,000 patients. And the trace lengths are skewed, but the majority are below 3 activities. And then we generated a process model. So because we need for our experimental settings always an event log and a process model, so we generated a process model out of those, out of 90% of this data set, because if we generate it about out of 100%, then we will have again a perfect model that is representing all of our event data. And we used actually those 2 different data sets for computing prefix alignments. And then we had different evaluation measures to reflect the quality of our approach. And these are the results. Here we have, on the x-axis we have, so these are for the synthetic data sets. On the x-axis we have the percentage of noise that we are adding. And on the y-axis we have the how much states are enqueued in order to apply our search algorithm. So that means here lower is better. So, and here we show that by using our upper bound approach for limiting the pruning, for pruning the search paths, we are saving a lot of space. So this is even more obvious when counting, or when counting the size of the queues that we were using. And obviously, when we increase the amount of noise, we will need more number of states to visit. This is also obvious to see when we count also the average number of traversed arcs while applying our search algorithm, but not as serious as in the previous case. But still, there is an improvement when we apply this parameter, so it's a useful one. And again, here we have the average number of visited states. I am afraid that this is a repeated one. No. Yeah, by adding the noise. And here we show, on the x-axis, we have the prefix length, because it's basically, because of the nature of the synthetic data set, we could control the length of the prefix alignments that we were performing, and we show here that the main message is that when using the upper limit, we are saving a lot of space, even with prefix lengths that are of 100. So this is on the average queue size. This is also obvious. And here we are testing the other parameter, so the window size. On the y-axis, again, we have the memory consumption, so lower is better. And the window size is deciding, as we have said, how long we are going back while calculating the prefix alignment for the new activity that we are receiving in the stream. So if we don't go a lot, we are saving a lot of space. But of course, as we will see next, this is not for free. So if we go more, we will need more space. So yeah, and this is actually reflecting the quality. So here, 0 means that it's a perfect alignment. So it's exactly as if we know what is there in the stream, and we apply it in an offline way. And we are comparing now the lengths or the costs that we are estimating to the offline ones. And we show here that when we have a very small window size, we have a very bad, like very high differences to the optimal costs, while using 20 is almost an optimal one. So, and these are the experiments on the real data set. And here on the x-axis, we cannot vary the noise because we did not add noise there. It's probably already there, but we have evaluated it only according to the prefix lengths. And again, on the y-axis, we have the storage that we are using, the space is used, and so lower is better. And yeah, so if we have a window size of 1, obviously we will be achieving the best because we are not using a lot of space. But if we have infinite size of the window, or if we are really going to the beginning of the stream to implement the prefix alignment, we will be consuming the highest space. And these are reflecting also the number of traversed arcs, so how much our window size is optimizing the A-star searching algorithm. And here again, we show very obviously that introducing the window is resulting with a gain there. Cost difference, here we show that, so here lower is better on the other side, so using smaller windows is resulting in bad results, particularly when we have the prefix length high enough, so like around 25. And these are a comparison with the conventional alignment algorithms, so not the prefix alignment, the conventional alignment algorithm that is in top there. This is the one that is using the most number of that is the most number of states and thus space that is needed to be visited, and the others are reflecting different versions of our approach, which are always better than the competitor, even with the window size of 20, which achieves a very good quality. And this is reflecting the number of visited states, which is basically similar to this value here. And finally, we have the costs. So the quality of the costs, how accurate we are estimating the costs. And again, here lower is better. And maybe the figure is not so clear, but smaller window sizes are resulting with an overestimating of the alignment costs. So to conclude, we have introduced a prefix alignment algorithm that is underestimating the true alignment cost. So that is exactly the benefit of our approach, that whenever we observe a deviation on a particular activity on the stream, we can safely signal an alarm and say that whatever the next will come on this case, there is a deviation in this particular case from the model. And that is exactly the main contribution there. We have introduced two parameters, the upper bounds for making our pruning effective, much more effective, and to use less space, and also the windows, which resulted in sometimes an over approximate of the optimal prefix alignment. In the future, we want to further investigate the trade-off between over approximation because of the usage of the window size, for example, and also the true alignment costs. And probably we want to take a look onto some theoretical memory bounds to show that we can, we have some proofs about the theoretical proof about how much memory we are using in our prefix alignment. Thank you for your attention and questions.